Hello. Okay, so that's all working. All righty. All right. So again, sorry about the tardiness this morning. There are mornings in which no amount of proactive planning is matched for the monument to frontal lobotomies that is the Northern Colorado Road and Transportation System. So,
It's too early to comprehend that statement. I'm gonna need you to simplify that. I'm gonna need to reduce it. Way too early for that.
all right, but the big thing that we're getting here, and this kind of closes out the course here a little bit, is polar coordinates. Um, we have been dealing up until now with Cartesian coordinates, also called rectangular coordinates, and we can convert these to polar coordinates. By the way, this is something that you see, you'll definitely see this in calculus, where you're sometimes dividing up the three-dimensional world not in terms of X, Y, and Z, three dimensions there, but sometimes you're dealing in cylindrical coordinates where you've got a, a an axis going in a specific direction, you've got a radius, an angle this direction, and actually a Z going up and down the axis there. Also, spherical coordinates are something that you run into as well. So there's a lot of ways to slice and dice the world, and it's not just rectangular coordinates for doing so. Along those lines, I'm giving you a point in two-dimensional space that is described in terms of polar coordinates. So I'm showing you square root of 3 and pi over 6. That is not x and y. Those are not x and y coordinates. Those are r theta coordinates. And how do we convert those to Cartesian coordinates? We just have some formulas that are associated with each one of these things. The x coordinate is r times cosine theta. And what do you think the y coordinate is? R times sine of theta. And as you can see, the first answer that we get is just 3/2. The second answer we get is square root of 3 over 2. And so we're able to write this as an ordered pair in Cartesian coordinates. You can actually plot these things in Desmos and confirm that they are the same point here. If I have, hopefully you know how to plot a point in XY coordinates in Desmos. If you make it so that you describe these things in terms of r theta, you can plot those points as well. I think if you do like r equals square root of 3, theta equals pi over 6. I'm not sure that switching it to the polar coordinate system is enough to convey that, but I'm actually a little shady on that. If somebody wants to test that out, that'll be helpful. In the meantime, do this one here. Convert this to Cartesian coordinates. In fact, let me try that. Try that, Desmos. The previous one was square root of 3 and pi over 6. Okay, so that's what it is in Cartesian coordinates here. If I switch this to polar coordinates, okay, it still's, so I have to say r is equal to that and theta equals that. Would that be good enough? Now it doesn't know what to do. Because it does understand this. doesn't understand the theta. That's right. It only understands the r. It says you can't graph theta as a function of anything that, and they say yet. So maybe that's an indication that there's an upgrade coming at some point. They've been saying that for a couple of years. Those are our two formulas there. So second one's easy. First one's kind of easy. All right, do we agree? Very good. All right, now let's go the other direction here. You're given something in XY coordinates in the rectangular coordinate system. And we want to convert that to the polar coordinate system. And so now we need some equations for r and theta. What's our equation for r? Zach, you know?
Square root of x.
Yeah. The distance from the origin. And the theta, actually what we find is tangent theta, which is equal to y over x. Okay, and so that's going to be equal to -1 squared plus 1 squared, which is the square root of 2. And then this one's going to be 1 over -1, which is -1. And so at first glance, this is, so you do this here. Arctangent of -1 is equal to -pi/4. But let's see which coordinate system we're in. Should I be in the fourth quadrant or the second quadrant? And the answer is that for -1, 1, I should be in the second quadrant. And so in reality, what this is 3 pi/4. So theta here is equal to 3 pi/4. And so my r theta coordinates are square root of 2 and 3 pi/4. So just a different set of formulas here for converting back. Oh, yes. And I can also do this as well. Oh, tangent is geez, the period of tangent is just pi. So there's no 2 out there. Okay. All righty. Convert this to polar coordinates. So really, if you plot your point, it becomes pretty apparent what it is. R here is equal to 2, and theta here is equal to pi/2. which is a little bit more useful than trying to use our equations here because we get tangent of theta is equal to 2 over 0, which is undefined. So we'd have to ask, where is tangent undefined? But yeah, r would just be equal to the square root of 2 squared plus 0 squared, which is just 2. All right, so let's just leave it. Leave it at that. Okay, good. Now, can we also do this with equations? The answer is yes. Here is an equation that is in Cartesian coordinates, and it's a familiar one that you've seen many, many times. Y is equal to x squared is just that usual parabola that is centered at the origin. It has a vertex at the origin, rather. What would this look like if I plotted, what would the equation be if I plotted something that looks exactly like this in polar coordinates? What would the equation have to be? Well, here again, we're making use of our conversion equations here, which I've listed to the right. And let's see if we can replace y and x with something over here. So actually do that real quick. Just plug those things in. Y is equal to what? And x is equal to what? See what we get. What do we get on the left? Are we not clear on what to do? Okay, good talk. What I want to do is where I got a y here, plug in r sine theta on the left-hand side. So I'm going to get r sine theta on the left-hand side. And where I've got an x on the right-hand side, I'm going to put r cosine theta. And that's going to be squared. Okay, so let me apply this squaring here to both of these. Okay, and what can I cancel from both sides? Olivia, what can I cancel from both sides? Hmm. So I'll divide by r. I'll just have sine theta over here. And I'll have r cosine squared theta over here. And let's solve in the same way that we solve for y to get mx plus b or something like that. Let's solve for r. Let's see what r is in terms of theta. I'll have to divide both sides by cosine squared theta. And I'll get sine squared or sine theta over cosine squared theta. There we go. Actually, let me represent this as cosine or sine over cosine times another 1 over cosine to get that cosine squared in the denominator there. Sine over cosine is just tangent, and 1 over cosine is secant. So secant tangent, that's the, if I plot that in polar coordinates, it looks like a parabola. Okay, let's try this one here. Convert each polar equation to a rectangular form. So what can I replace r with? Brandon, what can I replace r with? What can I replace r with?
With the square root of x.
Yeah.
That's fine.
Okay. I'll square both sides. Interesting. What does r equals 2 look like? What's the set of all locations that would have r equals 2? Yeah, it's a circle with a radius of 2, and it's centered at the origin. Is this not the equation from algebra for a circle centered at the origin with a radius of 2? Okay, so we're getting a tip of the hat from algebra here as well. But that's how we could represent this. Okay. Ideas on what we could do with the center one. Theta equals pi over 3.
Or arctangent.
Good. Along the same, it might just be easier for me to just say tangent of theta is equal to tangent of pi over 3, whatever that is, and then replace tangent with, this is what you were going with y over x. And what is the tangent of pi over 3? Square root of 3. Solve that for y? Huh. Tell me about this. What is this? What shape is that? Sage, what shape is this? If I were to plot this, what would it look like?
I'm assuming that this is it would be looking at the positive and not the positive and the negative because of the square root. So it just kind of looks, yeah,
Is the
basically.
x inside the square root?
It is though, yeah.
No.
No, is it not? Oh, no, it's not.
Okay.
Yeah.
This is y is equal to something times x, a number times x. What does that look like when you plot it? Algebra 1 here. Oh, come on, everybody. It's a line. It's a line. Thank you. Okay. Y equals mx plus b, and b is equal to 0. This is a line that is a slope of what? You're just not going to talk this morning. Okay, so that line has a slope of square root of 3, and it has a y-intercept of 0. I'm just going to lecture, I guess. So for this one here, r is equal to secant theta. I'm going to multiply both sides by cosine theta. Because if I do that, then I have r cosine theta on this left-hand side over here, and that's equal to 1. And r cosine theta is just equal to x. So this is a vertical line that crosses the x-axis at the number 1. Okay. Now let's go the opposite direction here. Convert each polar equation to a rectangular form. Okay, well, I can replace the r with this. And if I solve this for just sine theta, I get sine theta is equal to y over r. And so this becomes 6 times y over r. And actually, I probably should have done this first before substituting something in for r. So let's actually just keep this as r for a moment here. So I have r is equal to 6y over r. And if I multiply both sides by r, I have 6y is equal to r squared. And r squared would be equal to just x squared plus y squared. That's our equation. Okay. That's actually a circle as well. So we can basically introduce this new coordinate system called polar coordinates, and we can use algebra to convert back and forth between one or the other, either with points or with curves.
I think any of the offices over there would have an advantage because I have this slightest cut right here and it keeps getting touched every time I touch something.
Just looking around to see if there was a first aid kit. There is one in all of our high school classrooms. Yeah, why don't you just check to see in the office if they've got something there? All right, this is the last section here, graphing polar equations. So we're going to see what happens when we start to graph some of these things here. And it's really pretty cool, some of the kinds of shapes that you can get out of this. These shapes have new kinds of symmetry to them. Um, you can see here, for example, on this leftmost example here, this is a symmetry with respect to what's called the polar axis, or in our Cartesian world, the x-axis here. There's a reflective symmetry over that horizontal axis there. This one has a rotational symmetry with respect to the center here. Oops. And this one has a symmetry with respect to the y-axis in Cartesian coordinates, or the line theta equals pi over 2 in the polar coordinates here. Okay, and so what do these symmetries look like algebraically here? Well, the only difference between something that's up here and something that's down here is whether or not their theta value is positive or negative. And so a certain point r theta is going to be the same as a point r negative theta. Okay. And then also, if I make the the r value negative, then I can reverse it. Reverse it. How would I say this? If I add pi to this angle here, I'm switching sides from one side to the other, and so I just have to make r negative to make that happen. Let me jump to the one on the right here because that has a similar reflective symmetry just around the vertical axis. The difference here is that if I've got a value r theta here, that's going to be the same as negative r negative theta. It's also going to be the same as r pi minus theta. And here in the center here, r theta, as you can see here, if I rotate this around the center here, r theta is going to be the same thing as r pi plus theta. It's also going to be the same if I make r suddenly negative, and so I'm plunging myself to the opposite side. Okay, by the way, there actually is a name for this shape here that you see. I actually call this a cardioid. Why would we call it a cardioid? Looks like a heart.
Like a peach to me.
Yeah, I think peach is probably a
Looks
little
like a
little
peach
closer.
to me.
But this is our term for a cardioid here that you got in. And any time in which you're plotting sine or cosine plus something, and these two numbers are the same, you're going to get a cardioid that comes out of that. So if this number is slightly bigger, then you get a little loop here. If this number is slightly bigger here, then it doesn't actually come in all the way. It kind of looks like that. Yeah. So cardioid. Interestingly enough, just a little bit of trivia here. You've ever wondered why a heart doesn't actually look like a heart, a human heart? It's because it actually wasn't designed to be a heart. It was designed to simulate the shape of a woman's posterior, unfortunately. So it's a little bit of patriarchy that has been handed down, and we still have a little bit here. So I hate to break it to you, but in middle school, you were actually dotting your I's with little butts. So it's all part of the service here with Rose House of useless trivia. So, so graphing a polar equation by point plotting here. So let's actually see what this looks like as we plot this stuff here. Well, um, so we're given some values of theta, just like when we were plotting something in Cartesian coordinates. We started off with a set of x values, and you had to calculate what the y values are here. Well, the sine of theta being equal to 0 is just 0, so that's r of 0. Uh, Sine of pi is also 0, so I'm going to get another 0 over here. What are some others that are easy? Pi over 2. Oh, sine of pi over 2 is just 1, so this is going to be 10. Sine of pi over 4 is square root of 2 over 2, so that's going to be 10 times square root of 2 over 2. The 10 and the 2 will cancel out, and I'll just get 5 square root of 2. 3 pi over 4, the sine of that is also square root of 2 over 2. So I'm going to get the same answer here. Sine of pi over 6 is 1/2 times 10 is 5. Sine of pi over 3 is square root of 3 over 2, which times 10 is 5 times square root of 3. And I'll get similar answers here and here. 5 times square root of 2, is that 7 point something? I'm going to need some numbers, some actual.
7.07.
7.07. So I've got another one of those down here. How about 5 radical 3?
The 8.660.
Yeah, that sounds right. Okay, and then let's just plot these pairs here. 0 is 0. Okay. Pi over 6 is 5. Pi over 4 is 7.07. Pi over 3 is 8.66. So that's about there. Pi over 2 is 10, way up here. Okay. Pi over 3 is 8.66 again. That'll be nice. This is 7.07. This is 5. And this is back to 0. Oh, what kind of a shape did we create here? We have a circle. A circle that I know my circles are not
No, it
great.
just looks like a leaf or a flower petal instead.
That's just my drawing ability.
Yeah, okay. I was gonna say, it looks like a
I'll be dissing my drawing ability here now. I'm very sensitive about it. So no, it's good. So this is a circle here. Uh, specifically a circle that is centered around what in Cartesian coordinates would be the y-axis. And so that's what it looks like when we plot sine theta in polar coordinates. We get a circle. What do you suppose this is going to be? Think about what that's going to be there. Here, cosine of theta is cosine of pi over 2 is equal to 0. So, okay, this is going to be 0. Cosine of 0 is equal to 1, so this is just 10. Cosine of pi is equal to -1, so that becomes -10. Cosine of pi over 4, that's another square root of 2 over 2, so this is 5 square root of 2. Cosine of 3 pi over 4, now that's negative square root of 2 over 2 times 10, so we're now at -5 square root of 2. Um, Cosine of pi over 3 is 1/2 times 10 is just 5. Cosine of 2 pi over 3 is negative 1/2 times 10 is negative 5. Uh, Cosine of pi over 6 is square root of 3 over 2 times 10 is 5 square root of 3. Cosine of 5 pi over 6, that's negative square root of 3 over 2 times 10 is negative 5 times square root of 3, which, as I recall, these are 8.66 and 7.07. This is negative 7.07. This is negative 8.66. Let's plot those and see what we get here. So for 0, we're getting 10. For pi over 6, I'm going to get 8.66. For pi over 4, I get 7.1, we'll say. For pi over 3, I get 5. For pi over 2, I get 0. So I actually shrink to the origin here for that one. For 2 pi over 3, notice 2 pi over 3, you'd expect me to be in the second coordinate, but my value of r is negative, so I get plunged into the fourth quadrant here. This is negative 5. 3 pi over 4, this is negative 7.07. And lastly, 5 pi over 6, this gets plunged to the other side, and I plot negative 8.66. So interesting. Here's another leaf.
Oh, yeah, this looks like a lead,
You're actually quite right. So,
especially because we're gonna do the other shape, which is rose petal, which I did graph in Desmos.
nice. Oh, okay. So that works.
They do have two different graphs for
Yeah.
polar.
Yeah.
They have the onyx one, and then they have the rose one. I think this is the only
Yeah.
one that they have.
Nice. Nice. Very good.
You get to see it in motion too. So you can get to see it.
Oh, yeah. I love that.
Yeah.
I love that when you
She's
can do
just
that.
leaving it.
Yeah. That's great. Okay. So you can see we again get a circle, just one that is centered around the polar axis or the x-axis. Okay. So, cardioid is a member of a larger family of shapes called limicins. And limicins are basically anything that can be drawn by rotating a circle around another circle and having a pen be stuck out a certain radius from the center of the rotating circle. And it's tracing out a line that's like that. If the pen is being placed on the outer boundary of the circle, then we get a cardioid. If it's a little bit beyond that, then we get that extra loop in here. If it's less than that, then we get kind of like this sort of lumpy circle here. We also will have some other shapes that come up here, like rose petals here. Those are the things that Sage has already started to plot. A lemniscate here. This happens when we've got an r squared, usually uh, in the equation somewhere. R squared equals something, or r equals the square root of something like that. And then lastly, the spiral of Archimedes. R is equal to something times theta. That creates a spiral. The bigger that theta gets, the bigger that r gets. So it spirals out as we're moving around here. Actually, this is if you're wondering how pumps work, air pumps and the like, if you have an air compressor at home or something like that, they basically rotate two spirals around the center. So, because if you notice that if you follow some parcel of air through one of these portions here, you'll see that it's actually forcing the air into the center. So this is a nice streamlined way to pump something. Okay, so let's plot this out and see what we get here. So it's best to do the easiest ones first here. Cosine of pi over 2 is just 0. So that's just going to be 4. Cosine of 0 is equal to 1, so this is 4 plus 4. And cosine of pi is equal to negative 1, and so that's going to be 4 plus negative 4, which will be 0. Cosine of pi over 4 is square root of 2 over 2. Canceling that out with the 4, we get 2 square root of 2. We add 4 to that, whatever that is. Cosine of 3 pi over 4 is the same thing, except this is negative, and so this will be 4 minus 2 square root of 2. Cosine of pi over 3 is 1/2. So this is 4 plus 4 times 1/2. 4 times 1/2 is 2, plus 4 is 6. Cosine of 2 pi over 3 is negative 1/2, which when multiplied by 4 gives us negative 2. So 4 plus negative 2 is just 2. Cosine of pi over 6 is square root of 3 over 2, which when multiplied by 4 gives us 2 radical 3. So this is going to be 4 plus 2 radical 3. And in the same way, everything's just going to be negative in the second quadrant. So this will be 4 minus 2 radical 3 here. Okay, and can I get some actual decimals here for some of these things here? This will probably be, I'm going to guess, 6.8.
6.828. So
6.83. Very cool.
Yeah.
And for the top one here, 7 point something.
7.46.
7.46. Okay. So we start off with theta being equal to 0. The value of r is 8. Pi over 6, the value of r is 7.46. So about 7.5. Okay. Pi over 4, it's 6.83, so just under 7. Pi over 3, it's 6. Pi over 2, it's 4. 2 pi over 3, it's 2. 3 pi over 4, oh, what's this going to be? This bottom one here, I think is going to be 0.52. This one here is going to be 1.17, maybe.
It should be 0.535, so it should be 0.54. And then the other one was like 1.17.
Yep, very cool. 3 pi over 4, 1.17. 5 pi over 6, 0.54. And pi, we hit 0. So it's the upper half. Jeez. Hopefully your drawing ability is better than mine. This is the upper half of a cardioid. And if we allow theta to keep going here, we get the bottom portion of this as well. Let's actually see if we can plot this in Desmos here. Be nice. Sine or cosine?
Cosine.
Cosine. Okay. And there we go. And yes, if we want to, we could actually change these things to A and B to see what these things look like if we change A and B. So let's put B equal to 5 here. And let's put A equal to 5. As you can see, we get our cardioid here. What happens if I make A less than 5? We get this loop in the center here. And in fact, if A goes to 0, then this just becomes R is equal to 5 cosine theta, which is, oh, come on, be nice to me, is just a circle. So we're back here to 5. And so if we go back to 5, now we're at our cardioid. If I make it larger, now uh, the cleft part of the cardioid becomes less deep. So these are all the good way of describing all our family of lemniscates here. And we get a similar phenomenon when we make things negative. All right. Okay. So let's do this same one here, but let's see if we can use Desmos to figure out what this is. 1 minus 2 cosine theta. If I switch this back to Desmos here, A is going to be equal to 1. A is going to be equal to 1, and B is going to be equal to what now? Negative 2. Okay. So we've made the coefficient on cosine of theta negative, and so it's switched it to the other side here. So kind of a cool set of shapes here. Notice if I make B go to 0, then it just becomes R equals some constant, which is just a circle. Let's see what happens when it's not cosine theta, it's cosine 2 theta or cosine 3 theta. Actually, I'm going to have you just experiment with that. So pull up Desmos and see what it looks like when you plot cosine of 2 theta, cosine of 3 theta, cosine of 4 theta, and so on.
If even numbers twice their value and odd numbers are their value.
Yeah,
Like
yeah.
circle.
So for example, if I plot how many petals will cosine of 3 theta have?
Three.
3. And we kind of went halfway there. If I kept on going here as far as plotting these things, I would have gotten something like this. So a total of 3 petals here. How about cosine of 5 theta? How many petals? 5. Okay. Let's try even numbers here. Cosine of 2 theta.
Four.
4. Interesting. So we double it when it's even. Cosine of 4 theta? 8. So there's two different rules going on here. If it's odd, then it's the same number of petals. If it's even, then things double. So along those lines, predict how many petals you would see for this next one. The rules are same for sine and cosine. How many petals would we see?
Six. Or three.
3 is odd, so
Oh,
just 3
the
petals.
two multiplies the magnitude of the
Yeah.
petals and the number of them.
Isn't that what you said?
No, I thought the magnitude affected the petals for some reason.
Magnitude. Oh, you
But
mean
it's
the amplitude outside
the
here?
amplitude, yeah.
Nope, that doesn't affect it. So number of petals is affected by what's inside the sign here. So we're going to have 3 petals. How does this one look relative to this one? 2 sine 3 theta versus 2 cosine 3 theta.
Offset.
In what way?
Well, it's kind of like shifted up.
Mm-hmm. They both have 3 petals, don't they?
Mhm.
But the one for cosine kind of looks like that. All right, let me change color. And the one for sine, I don't know why this thing's not working for me today. But I just don't get it. I changed the color. I guess not. The one for sine is going to look like this. Okay, so the one for cosine has got a symmetry with respect to this axis. The one for sine has got a symmetry with respect to this axis. The one for cosine splits this petal down with the x-axis. The one for sine, splits a petal using the y-axis. Okay, so based upon what you have been able to explore here, let's see if we can come up with some general descriptions of the following here. What is A control? First of all, what's the shape of this?
The petals. They're like
Sine of 1 theta. This is just a circle, as is this one. So this is a circle along the y-axis. This is a circle that's along the x-axis. And the circle has got a radius that's equal to A. Okay. And for something like this, if n is even, then how many petals do we have? Brendan, how many petals do we have if n is even or n is odd? Here's n where. Okay, so if it's odd, it's just n petals. If it's even, what happens? It doubles. Okay, and I think we'll probably skip that. Lemniscates, these things generally have two petals to them. You can plot these things in Desmos and see what they look like. Okay, so you can see this is what the first one looks like. Two petals going in this direction and this direction. If A is equal to 10, then it's enormous. If A is equal to 8, same thing, just a little bit smaller. So this function, this part of the function here kind of acts as an amplitude, very much like what we've seen before. Okay, and if we switch this from sine to cosine, let's see what this looks like. Hmm. Same kind of thing here, except it's along the x-axis here. It's rotated a little bit. And again, if A is equal to 8, it's a certain size. If A equals 10, it's a little bit bigger. So I can tell you on the test what kind of stuff, what kind of questions you're going to have to answer. You'll see a picture of something and you'll be asked to say, what form is this? Is this, you know, 2 plus 2 cosine of theta? Is this the square root of cosine? Something like that. So you just have to be able to recognize what these things look like more than anything. Be able to do a matching problem or something like that. Okay, what do you think this is going to look like? How many petals? Or this two is even? And how far out are those petals going to go from the center? Three. Exactly right. So four of those, and uh, one of the petals, let's see what this is going to look like here. Is 3 times 2 sine of theta. Nice little four-leaf clover there. What do you think that looks like for cosine? Yeah. Also a four-leaf clover, just offset just a little bit, just spun a little bit. This reminds me of that game that I remember was on TV a lot when I was a kid. These plastic things that you can use to draw different shapes. I think it's called Spirograph. Something, it was a toy, yeah, that you could use to draw really cool shapes.
I think I remember what you're talking
Yeah.
about. I think
So same idea here. Ooh, but this is r squared. Let's see what this looks like here. Let's take a look at what r equals 16 2 cosine 2 theta looks like, and then let's see what r squared of that looks like. Okay, so this is what it looks like if r isn't squared. If r is squared, must be linear in r. Okay, so I've got to stick a square root on the other side. Okay, so good example of a lemniscate there. Not a, yeah, lemniscate. So see what that looks like. And for sine, it just looks rotated a little bit. How is this used? I'll tell you how it's used. At some point in science class, you were told that an atom has protons and neutrons at the center, and the electrons were presented as these little planets that were going around the center of the circle. That's sort of right, but we were sort of lying to you when we gave you that simplistic of a model. When we're dealing with things that are so small, one of the things that quantum mechanics shows us is that basically everything gets really, really fuzzy. It becomes uncertain where the actual location is of something. And so the electron is described more as a wave, a cloud of possible locations when that happens. And what do the shapes of those clouds of locations look like? Well, as you can see, many of them have symmetries that can be described using some of the equations that we have here. You see this in chemistry when you are describing s bonds and pi bonds and d orbitals and these different kinds of ways in which atoms connect with each other. Those things have different shapes to them. So we have these shapes of location, basically states, quantum states of electrons going around the most simplest of atoms, which is the hydrogen atom. And it's a little hard to describe these things in terms of a singular point that's orbiting around the center here. But if it's a wave that's sort of pulsating around this thing, then it's a little bit easier to visualize and far closer to what is actually true in reality. Okay. So yeah, everything is a wave. Everything has a certain degree of uncertainty in its location or its energy. In our physical world of macroscopic behavior, that those things are so small that we never really have to contend with them. But when we're dealing with things that are this microscopic, then suddenly we do. Okay. Tell me what the graphs are of these kinds of equations here. What's the top one?
Circle.
It's a circle of radius what and center at what?
Ooh,
Circle radius equals 2, centered at where?
0, 0.
0, 0. This is also a circle. What's its radius?
But
5. Square root of 25 here. And where is it centered?
there's
-6, 0. How'd you get that? Yeah, exactly. So um, the general form of this equation here for all circles is x minus h squared plus y minus k squared is equal to r squared, where hk is the location of the center. Now, if it's located at 0, 0, then those two hk's drop out. We just have x squared plus y squared. But when that's not the case, what kind of a shape is this? That's not a circle. That's an ellipse.
And the
Last one is a hyperbola. Good. So this is an ellipse here. You can tell because it kind of has two, and I'm going to use air quotes for this, two radii, one going in one direction and the other one going in the other direction here. And so where's this centered at?
it's five. Because they're
No,
they have it backwards.
no, we still have h and k to contend here. So it's centered where? -6, +7. And it's got a major axis in the horizontal
I was thinking
direction.
about those two.
Yeah. And it has a minor one at on the y-axis of 3. Then lastly, a hyperbola has a center here at -1, -3. And it's got, again, it's got major and minor axes here that are based on this 49 and 4 here. So I think that's 7 and 2. All right. When do we see ellipses and hyperbolas? Ellipses would probably be an easier one to answer. An orbit. In elementary school, when you were presented with planets going around the sun, we presented them as circular orbits. That's sort of true, but we were sort of lying to you there. They're actually closer to being ellipses. They're actually not exactly ellipses either, but it's closer to the mark to say that they're ellipses. So they're sort of oval shaped. A hyperbola, along those same lines, a hyperbola, if you recall, kind of looks like this. And so if we see something that's going through our solar system that kind of has this sort of trajectory as it's going through, just one of these two, one side or the other, if it has a hyperbolic trajectory, then we know that it's not something that is a resident of our solar system. We know that this is an interstellar particle that's coming from outside the solar system. And we've actually been able to detect a few things that are interstellar objects floating through our solar system and be able to identify them as such based upon the fact that they have a hyperbolic orbit, not an elliptical orbit. Okay. So all of these things are families of the same group of shapes called conic sections. Take a look at this here and tell me what kind of a shape do we see here on some of these? If A is equal to C, if A is equal to C, then I could divide both sides of the equation by A. I'd get and I get an x squared plus a y squared. What kind of shape is that? Circle. If A times C equals 0, that means that either A is equal to 0 or C is equal to 0. Let me erase. If A is C is equal to 0, then either A equals 0 or C is equal to 0. So one of these two things drops out. So we either have an x squared but no y squared, or vice versa. So take a look at this problem here. If I move this y to the other side here, and I've got x squared and x and f, what kind of shape is that? It's a parabola. Yeah. So this first, yeah, it'd be a vertical parabola. And if A is equal to 0, now it becomes
Then if it was like y squared, it's horizontal.
horizontal parabola. That's right. So this first one was a circle. The second one's a parabola. Let's see if it'll allow me to erase now. Okay, good.
Not been a day.
This has not been my day for technology. Okay. If A times C is greater than 0, then these two things are the same sign, and we'll assume that they're positive, because if they're negative, we could multiply everything by -1 and make them both positive. If they're both positive, then we have a plus in between the x squared and the y squared. What kind of shape is that? That's an ellipse. And similarly, what do you think the last one is? It's a hyperbola.
And I think there was some rule about the hyperbola that if there's something specific, I think after x was calculated.
Yeah. So a hyperbola can either look like this, or it can look like this. If the x squared is first, it looks like this. If the y squared is first, it looks like that. Okay. This is not something we're going to get tested on here. So I'm going to leave this as it is. I think that's as far as we're going to take this here. But yeah, well, I mean, it's a review just so that we can do some of the stuff here. 4 sine theta, what's the shape of that going to be?
That's a circle with.
It's a circle. Yeah. Circle with a radius of 4. That's moving along the y-axis. How about this one here? What's this going to look like? We're not into the petals yet. Circle with a radius of 2 along the x-axis, the polar axis, we would say, but on the left side or the right side? Left side, good, because of the negative, yeah. Theta is equal to 2 pi over 3. And notice, take a look at this coordinate system here. What would theta equals 2 pi over 3 look like? Is this point on theta equals 2 pi over 3? Say yes, Professor Withrow. It certainly is. Yes. Is this point on theta equals 2 pi over 3?
Yep. It's a line.
And it's a line that's just along this right in here. So theta equals something is a line that's going through the center, and it's along, one of these radial lines here. Same thing with 11 pi over 6. That's going to be, just a line that's going in that opposite direction. R is equal to 4. What's that going to look like?
Circle.
Circle with a radius of 4. Yeah. Centered at the origin. Yes. Interesting. This looks cool. Check this out. This one's a little bit surprising. 4 cosecant theta. If you plot that, what does it look like? Yeah, a line. Vertical or horizontal? Horizontal. Why? Can we see why?
Because if you multiply both sides by sine theta, it Yeah, R sine theta. F X equals
Actually, r sine theta is equal to or y. Yeah. So this is just y equals 4. It's a horizontal line. What do you think secant would give us for secant theta? Not y equals 4, but the x equals 4. Yeah. So secant and cosecant in polar coordinates become straight lines, horizontal or vertical. So yeah, this would be x equals -3 here for this next one. Okay, I think that's pretty much as far as we need to go there. Some of those. I usually like to end the class with a sort of collage that kind of gives us a bird's eye view of all the stuff that we've covered. These trig functions can be understood in multiple ways and can be applied to a large number of circumstances here. Um, we've seen a number of instances in which they can be used to find angles and distances that can be useful in construction. We've also been able to apply them to the circle, in which we can describe things like harmonic behavior here. Um, in addition to being able to describe things in terms of construction or in terms of surveying, we can also take a 3D model of something and figure out from the point of view of somebody, what's the angle to this object, what's the angle to that object, and so on, which enables us to be able to draw scenes like this in some kind of any kind of a video game that's 3D and that involves the camera um, following kind of a third party character that focuses on the characters that are playing the game. We can also see this when we're traveling. This is following the same inverse tangent function that you are using to figure out field of view. We've also been able to apply these things to complex numbers. And for example, the complex plane, if we start to talk about how quickly complex numbers, if you multiply by something and add something, how fast they approach infinity, we get this very, very complex, infinitely complex fractal shape here that is quite lovely and quite incredible. We've also been able to have a way of describing things that are vectors, things that really require a magnitude and a direction to be able to describe what's going on. These vectors can be, at least in two-dimensional space, can give rise to means by which we would add two vectors together and make use of complex numbers to be able to do so. And then lastly, we took a look at polar coordinates and found that there was another way to slice the two-dimensional world. And as you would see later on, the three-dimensional world. Okay, so quite a bit of stuff. Not bad for a summer. That's all I've got for you, which is probably be good because my computer is just completely going nuts right here. So you've got about a half hour. Let's take a look at how things are looking with regards to the course. Okay, so you've got recitation 3 that's due tonight. You've got a couple of problem sets involving polar coordinates that are also due tonight. There have been some review assignments here for the final. Two of them were due Tuesday night. I'm willing to move some of these things if it turns out that's helpful or necessary. But there are four review assignments in preparation for the final. So what would you like me to do?
I think it'd be nice to review them again.
Uh,
Or look
but
at the-
should I'm asking if I should move their due dates.
Which ones exactly? There's
You tell me.
all of the reviews or, because a Sunday review day would work for me. Where I can do all of the reviews on Sunday. That way I can prepare for.
So it sounds like you're asking me to move review chapter 1, review chapter 2, and review chapters 3 and 4, part A to Sunday night.
That way I can
What
do.
do y'all think?
An entire review.
I can do that. Yep. So I will. It's one of the things I love about this software here.
And that way I can spend one of my days left just reviewing.
Sounds good. Okay. And again, the final exam is going to be 2 hours long, very, very much like one of our tests, 2 hours long and twice as many problems, and it covers the whole class. All right. So we kind of have some unstructured time right now, in which I might walk around and see if I can help out with anything that you're doing here. We basically have a half hour left of class time. So go through each one of those review assignments there and see if you've got any questions about those things. All right, sounds great.